Hello everyone, I'm Dr. Arshad, computational plasma scientist working at Quantemol, and today I'm going to talk about assembling and optimizing plasma chemistry sets using QDB. So QDB is a Quantemol database which has a set of chemical reactions, and my goal today is to give you overview of how QDB could be useful for simulating any plasma-based applications. So let's start. Setting up the plasma chemistry is one of the crucial steps for any plasma modeling. So QDB offers very efficient way of setting up the chemistry, and there are two methods basically. The first method for setting up the chemistry is referred to as all-in, and the second method is referred to as step-by-step. So in the first method, you can simply create all the reactions and species found relevant. And the advantage of this method is that this is very fast, and the downside would be it's hard to identify problematic reactions, or the missing ones, or the duplicate ones. This is suitable for 1D, 2D, or 3D. In the second method, step by step, you can start with one feed gas and add reactions one by one. You can repeat the same procedure for other feed gases as well, and then you can add cross sections and the reactions for the resulting species. The advantage of this method is you have more control, in the sense you can easily identify problematic reactions or the missing ones. And the downside of this method is it takes more time to set up the entire chemistry process. How do you get the relevant data? Well, QDB offers access to more than 25,000 reactions. QDB offers access to cross sections and the rate coefficient for more than 25,000 reactions, and it also offers access to pre-assembled chemistry sets and species data such as enthalpy of formation or the surface coefficients. So this is a screenshot from the QDB website. So the user can create his own chemistry set using QDB app. So we have QDB app as well. Requirement: the user can use the chemistry tab as shown on this screenshot. Using this tab, the user can create the chemistry sets as per the simulations, and you can test it via 0D simulations. So every plasma simulation consists of two parts: physical model and the chemical model. So the physical model describes the physical parameters such as particle density, particle transport, electromagnetic fields, and these parameters should be chosen based upon the simulation, the speed of the simulation, and the accuracy. For example, if you are dealing with high pressure regime, which is more collisional, you can go for the fluid modeling. If you're dealing with the low pressure regime where the continuum mechanics breaks down, you can go for the PIC modeling or the DSMC. And if you're dealing with the intermediate pressure regime, you can go for hybrid modeling. The second model, the chemical model, describes the chemical reactions occurring in the plasma mixture via a set of neutral species, excited species, electrons, and the ions. And these species can lead to electron impact collision or the heavy particle collision. So in the subsequent slides, I'll be showing few examples which demonstrates the effect of electron impact collision and the heavy particle collision on the physical model. In today's presentation, I'm considering only three electron impact collision, which is excitation, ionization, and the recombination. Well, there are other collisions as well, such as the dissociation collisions and all, but these three collisions happens more frequently in the plasma mixture, so my focus is only these three collisions. Let's look at the electron density. So the figure on the left shows the electron density for excitation variation case, and the figure on the right shows the electron density for ionization variation case. This is only for simple argon model. So in both the cases, we varied the collision cross section to get these bar graphs. So if you look at the half excitation case, it has slightly higher density, electron density, and as you increase the level of excitation, electron density drops. Whereas the reverse is the case for ionization. Lower the ionization, lowers the electron density, and as you increase the level of ionization, the electron density is increased. So basically, excitation events have a larger influence on the electron density than the actual ionization process, because of the way the energy is distributed or consumed in the plasma. So when electron collides with heavy particles, it can lead to excitation or it can lead to ionization. However, the energy required for excitation is relatively lower, so most of the available energy is utilized for excitation events, and because excitation happens more frequently, it affects the overall energy distribution in the plasma. So if the electron density looks slightly off, we should turn our focus to excitation and the dissociation reactions, because if the excitation and the dissociation reactions are more dominant in a mixture, that means very low amount of the very low amount of energy excitation. So you have that impacts the electron density overall. Let's look at electron temperature now. So the figure on the left shows the electron temperature for excitation case, and the figure on the right shows the electron temperature for the ionization case. This is for the same simple argon model. So from here to here, we basically varied the ionization cross section. We doubled the ionization cross section. So as you double the ionization cross section, this changes the source term, and to maintain the electron production and the losses, electron temperature adjusts itself in the sense that it drops to maintain the production and the losses. As you increase the ionization further, source term gets changed further, and the electron temperature drops to maintain the balance between production and the losses. Whereas if you look at the excitation case, changing the excitation does not significantly impact the source term, so therefore the production and the losses are already balanced, and the electron temperature remains nearly same for all the cases. This figure shows the electron temperature versus power for CF4 and O2. So the red line shows the CF4 with negative ions, and the blue line shows the CF4 without negative ions, and the green line shows the O2 with negative ions, and the yellow line shows the O2 without negative ions. So in general, the presence of negative ions increases the electron temperature, because when you introduce the negative ions in the plasma mixture, that increases the electron loss via electron attachment, and this leads to high electron temperature. So if the electron temperature looks off, turn your focus to electron production and the losses term. Let's look at heavy particle collision. So the heavy particle can undergo ion-ion recombination, it can undergo symmetric charge exchange, asymmetric charge exchange, it can undergo electron detachment or the penning ionization. So this figure shows the impact of asymmetric charge exchange collision on the relative ion density. So we consider O plus and O2 for charge exchange. So this is number density versus power. The yellow line shows the O plus without any charge exchange collision, and the blue line shows the O2 without any charge exchange. So when O plus collides with O2, O plus becomes a neutral oxygen atom and O2 becomes O2 plus. So because O plus ion density comes down as it becomes neutral, so you see this green line below the yellow line, and so O2 becomes O2 plus, so its ion density increases, so you see the yellow line above the blue line. So this figure shows the electron detachment for excited case for O2 negative ions. So this is number density versus power. The blue line shows the O2 negative without excited state, and the yellow line shows the the red line shows the O2 negative. So the presence of excited states makes the species unstable, and it has more tendency to lose electron by electron detachment. So that's why its ion density comes down, and this is not the case for the ground state, and its density remains higher. How do you optimize the data set for given process parameter? Well, the data set in its current form has more reactions and species than actually necessary to predict any process parameter. For example, if you want to predict the density of neutrals reacting with the surface, the data set is surplus, which is unnecessary. Additionally, the coefficient describing the surface parameters, it might be missing, or it might be unknown, or it might be inaccurate. So the QDB tool offers the QDB offers it offers tools to optimize the data set and fill the missing data, or you can calibrate the data. The first optimization technique is referred to as set reduction. So the data set can be reduced as per the requirement. So this window shows the removed species from the total set, and the window in the center, it shows the user can keep the species as required for the simulations, and the third window shows the error induced depending upon the species. For example, if you are considering only NH, this figure will show you the relative error induced while considering NH compared to the full data set. The same is depicted in the color coding as well at different power levels. So the green color shows that the error is less than 10%, while the red color shows the error is significant, more than 10% in this case. The second optimization technique is referred to as surface coefficient variation. So this is very helpful while you're dealing with the etching or deposition process. So in this technique, the user can run automated variations of surface coefficient. So the user can vary only the sticking coefficient, the user can vary only the return coefficient, or the user can vary both the parameters. The figure on the right shows the NH density at different power levels. To get these figures, we kept the sticking coefficient constant, and the return coefficient was variable. So this was for NH produced by H at the surface. The third optimization technique is called surface coefficient calibration. So using QDB app, the user can fix the input target density and find the coefficient pair which best reproduces these densities. So the red line over here, it shows the target density, while the blue line shows the calculated NH density at the optimum coefficient. So this was for NH produced by H at the surface. So the user has the user can optimize only the return coefficient, or the user can optimize both the parameters. We also have a machine learning model for estimating rate coefficient. This individual named Martin has developed a machine learning model, and my colleague Dr. Katrina, she has improved the model to estimate rate coefficient for binary heavy particle collision. So this algorithm is already embedded in the QDB website and available via QDB app. So the user can sign up for free using this website, and has the user can access to this algorithm via after signing up. This is work in progress. We are also developing radiative database for predicting emission spectra. This is still under development. So basically, it will be collision radiative model for predicting optical emission spectroscopy. Currently, it contains information about molecular and the atomic transition. So it will be included in the coming weeks. Yeah. Thank you.
Thank you, Arshad, for the presentation. If anyone has any questions for Arshad regarding the QDB, we have some time to answer a couple of questions, so please let us know. If not, we will move to our next talk, which is by our guest speaker, Dr. Harm Noops.
Thank you.
Hello. Yes, let me. Yeah, maybe I don't know. Actually, maybe I had a question. I don't know if anybody else had a question. I was wondering about the NH production. What do you think is in these kind of simulations or these kind of plasmas the main route for NH? Is that happening in the plasma? You mentioned by hydrogen. So what is the hydrogen reacting with to make the NH?
I think it was nitrogen and hydrogen reacting to form the hydrazine, actually.
Ah, okay.
Yeah. If I might chime in, since I actually did the simulations, this is an N2H2 plasma at low pressure, so it's actually mostly produced at the surface.
Okay, I'm turning up my volume. It's a little bit, I think Arshad was very loud, so I turned down my volume. Could you repeat that, Sebastian?
Yeah, I did actually these simulations. So this is an N2H2 plasma at rather low pressure, so the NH species are mostly produced at surfaces.
But then as a radical, do they leave the surface, or do they leave as NH3 and are then dissociated in the plasma?
Sorry?
Do they leave as an NH from the surface, or yes, do they leave as an NH3 and are dissociated in the plasma?
Well, in this specific case, we did that. As I said, this is just a kind of test simulation to kind of demonstrate these capabilities. So for these, we just on the surface.
Okay. Yeah. I have this kind of, my gut feeling would say radicals don't leave the surface as radicals, but would leave.
Yes, might be, but as I said, this was not intended to be a kind of realistic simulation, just as for